Anyone can tell me whether you got that link? Unmute and then say whether that Madam class people, anyone joined here? Hello? Hello? Anyone can unmute and then tell me whether Madam class people also joined here? Whether you got the link? I am audible? Whether I am audible? Hello? Whether I am audible? Anyone can unmute and then tell me whether I am audible? Okay.
Yes, sir.
Thank you. So whether that link is shared for that class also, that's why I want to confirm. I want to start before that. The students from Madam LLC Madam students have joined or not? Anyone from that class? Okay, I will start. Okay, no problem, no issues. I have posted the link. So, so today we are going to start with whether my slides are visible. I am audible. Whether
Yes,
my
sir.
slides are visible. Okay. So last class, Madam taught you that fourth unit, 10 optimization technique. So in that, one of the topic is memory hierarchy design. So memory hierarchy design, we are going to review of memory hierarchy design. In that cache performance, basic cache optimization, all those things we are going to discuss now. So in that memory hierarchy, so you all know what is basically memory hierarchy, but I want to give some detailed information about that memory hierarchy. So if we are referred to a processor, one of the basic requirement is memory. So in that case, memory, we are going to say hierarchy means in what way the memory is closer to the processor. In that order, we are going to list. This is the hierarchy. Anyone can tell me which one will be the highest hierarchy related with memory concept? Which one will be very closer to the processor? Anyone can tell me?
Registers.
Very good, very good. So register will be very close. The next hierarchy will be given to cache, and then next hierarchy will be that primary memory, and then next will be that secondary memory, all those things. So in that case, why we have to go for memory hierarchy, we have to study. So whenever we are going to work with any system, the programmers always want to work with in that high speed. So that is why we are going to say that is going to be called as performance. So whenever we are talking about system, in that case, the system has to be work as much fast along with the memory. So whatever, whether I am going to work with CPU or otherwise I am going to work with memory, it has to provide maximum speed. So in that case, if we are keep on going to increase the speed, automatically, indirectly, it will increase the cost also. So that factor also we are going to consider whenever we are going to improve the performance of any system. So in that case, if what is the best solution? So I need high performance. So high performance in that sense, with high speed. Another important thing, with minimum cost. So affordable cost. We will say we should not use that word minimum cost. We have to go for affordable cost. So in that case, the best economical solution is memory hierarchy. That is why we are going to look forward for this particular topic, memory hierarchy. So in that case, memory hierarchy exploits two basic principles. One is going to be called as temporal locality. One is going to be called as spatial locality. So what is going to be spatial locality means? So it is likely to access the same address soon again. So for example, if repeatedly I want to use some address. So in that case, I want to keep it as closer. That is going to be called as temporal locality. And then whenever we are trying to talking about spatial locality access address, whenever, for example, if I want to use in future, so that is also going to be stored in a particular manner. That is going to be called as spatial. Frequently we are going to use, that is going to be called as temporal locality. But some cases, for example, we are going to use it for after 10 iteration or 10 cycles. So that is going to be stored in a particular memory location. That is going to be called it as spatial. But if you refer to this meaning, sometimes it is going to be closer, but some small what we can say, there will be small deviation, which means that according to the internal processing of a particular processor architecture. So which is very closer, which is not very closer, but it will be kept somewhere else, where it is not going beyond some level. So it will be somewhere within that particular boundary. So that based on that, we are going to differentiate. This is going to be called as temporal locality. This is going to be spatial locality. Okay. The next one is, this.
Sir?
Yeah.
Sir, some bell sound is coming, sir.
Yeah. Okay. I will try to stop that one. Thank you. 1 minute.
Thank you, sir.
Okay, I think now I will continue. Sorry for the disturbance. So that is spatial locality. I am audible now?
Yes, sir.
Okay, thank you. The next one is that most of the time the processor going to spend 90% of time. So 90% of time executing the 10% of code. So for example, what we can do is we are not going to use the entire code. So we have a small portion that is going to be used. Sometimes it will be repeatedly used. Why? Because we will call that function and then we will going to execute that particular function, or sometimes. Okay, so depends upon that particular design or for example application, it will be varied. Okay, but this is one theoretical aspect, but it is time to time it is going to vary. But no need to give more importance here, but we have to study about memory hierarchy. So in that case, memory hierarchy is going to be organized into different levels. So we already I told you we have different levels. We are going to see what are the different levels, all those things. So in that case, how we are going to fix that particular levels is whether it is smaller, that size is going to be smaller, and then it is going to be whether it is going to be faster, whether it is going to be more expensive. Based on that, we are going to categorize into different levels. So this is going to be in small size. It is going to be in first level. So it is going to be in faster. So that case we are going to fix in this particular level, something like that. So based on that, we are going to fix the level. We are going to have different level, but you can ask one question: how we are going to fix this is going to be the level. So for that answer is very simple. It is going to be smaller. That is why it is going to be. So if you refer to register, it is 8-bit or 16-bit. So in that case, it is going to be fixed in that first level, something like that. Faster, speed, catch is going to be speed, something like that. So more expensive. That is why I am kept it here. So I have an external hard disk. That is why it is going to be kept this way in this particular level. So that is the example. Okay. So lower level is farther from the processor. So we have some lower level that is going to be kept in that particular position. What is a goal? What is the goal I have to find this? that memory system cost per byte. So cost, what will be the how much I'm going to spend for in order to store one particular byte. So that is going to be called as cheapest level. So I will keep one byte information. So that is going to be kept, and then that is going to be accessed as much as fast level. So how much amount I'm going to spend for in order to store one particular byte, how fast I'm going to access that particular byte. That is my goal. So cost is also has to be minimum and then has to be fast. So that is my ultimate aim for in order to, for example, in order to fix the memory I got it. So in that case, there will be one thing called as inclusion property. So whenever I'm going to check for a particular data, if it is not available, immediately it will be, we have to check for the next level. That is going to be called it as inclusion property. So I will check with the cache. If it is not available within the cache, so in that case, I will check for the next level in that main memory, or otherwise level 1 or level 2, something like that. Or otherwise, always required for the lowest level. I will always, I have to keep in the lowest level because it will be much faster. So that is why I am going to keep always required at the lowest level. So, for example, in server as well as desktop, we are going to use this storage at lowest level, while that personal mobile devices is flash. This is one in theory. So we are going to have this storage. We are going to use server. What is that? What type of memory I'm going to use? For example, whenever we are talking about personal mobile devices, what will be the storage we are going to see? But it depends upon the technology. It is going to be vary. So here, if you refer to this memory hierarchy, so I will keep registers. That is going to be, for example, memory hierarchy for a server. So in that case, I will keep the register with the lowest level, and then I will keep that next level will be level 1 cache. If you refer, that size of that thing will be very minimum, and then the time for latency will be very minimum, 1 nanosecond. Whenever we are talking about level 2, so in that case, that size is little bit high, but it will take some amount of time. So this is where this hierarchy is going to be there. So here that storage is going to be more, but that network latency, that latent propagation time, it is going to be more. So finally, I will keep disk storage. So disk storage is going to be there. So already I told you, in that previous slide. So desktop use that server and desktop use disk storage at lowest level, which means that that it will be the last level. We'll call it as. So at last, for example, I will keep as a storage level. So lowest level means don't keep. That will be the lowest level. So hierarchy register will be the highest level, highest hierarchy. That lowest level will be given to this storage. So whenever we are talking about personal mobile devices, so we here also will have level 1 and then level 2. We no need to use level 3 because the size will be more. So, but here we are going to use the lowest level. We are going to use storage, flash memory as a reference. So this is one diagram which will help you for memory hierarchy. So what will be the memory hierarchy we are going to use for in order to use a server as well as personal mobile devices? If you have any doubts, if you stop me here. The next one is performance gap between the processor and memory. This is one chart, that graph it will show. Whenever we are talking about processor, what will be the accessing memory? What will be the speed? What will be the performance? So every year it will be keep on increasing, that accessing memory requirements per second. So for example, 1 clock cycle, how much memory I can access? So that's why I told you, if we go with that 80-85 initial stage, so that at 1 clock cycle is required for another to access 8-bit, one memory location, that maximum data I will get 8-bit information. So the next level, now 1 clock cycle, that 16-bit processor, the processor, it will access 2 byte of information. And then 32-bit processor, 1 clock cycle, for example, 32-bit, 4 bytes of information, something like that. So if it will be keep on increasing. Whether my recording stops?
No, sir.
Okay. So in that case, this this is the requirement. So if that processor cycle according to that, how much memory location I'm going to access, that is going to be. So whenever we are talking about DRAM, that is also, it is going to be access number of memory location I'm going to access in term, and in particular second, it is going to be that. Normally we will use the term cycle of one cycle, how much memory location I'm going to access. So based on that, I'm going to fix that performance. So that is why now people are not using 8-bit processor. Now we are going to use 32-bit processor, 64-bit processor. Why? Now one cycle with 64-bit, that is the processor performance. So now here we are talking about what is the memory wall. What is memory wall? Bandwidth. So what will be the bandwidth? So how much memory size? What will be the memory size? So in that case, that size also has to be. If you feel a little bit fast, I will go slow. Okay. If I'm going to access a particular memory, what will be the size? So based on that, I will fix that memory bandwidth. That is going to be peak bandwidth. What is the maximum memory size I can access? So in that case, whenever we are talking about memory, even though memory is going to be very important, but whenever the design point of view, reducing that memory access will increase the performance. Why? So if I'm going to use a memory, I have to give the address, I have to fetch, and then I have to decode, and then I execute. So in that case, that is why people are using cache as well as registers in that load store architecture or otherwise RISC architecture. But we'll try to optimize. That is why here we are trying to optimize the average memory access time. So we have to reduce the time. So that is why we are not going to use disk to storage and all. We have to come out with registers. We are going to use more registers. We are going to use caches in order to store the data. So that is why we have to reduce that optimize. Optimization can be done based on the timing access. So in that case, whenever we are talking about average maximum memory access or average maximum memory access time, we have to consider some of the attributes. What will be the cache access time? And then whenever we are talking about what is the miss rate, what is going to be miss penalty. We are going to see what is basically miss rate, what is miss penalty, all those things. Okay. As of now, 3 attributes you have to think. One is going to be called as access time, miss rate, miss penalty. Access time, already you all know. So if I am going to get one instruction, if in that case, how much time it will take for in order to access that particular instruction, or otherwise how much time I took for in order to execute that particular instruction. So based on that, that is going to be vary access time versus execution time. Access means how fast I will retrieve, how fast I will fetch as well as decode that particular instruction. That is going to be called as access time. So in high-end processor, there may be 10 MB or more than on-chip cache, and large as well as second or third level cache. So whenever we are talking about the latest i3, i7, that case, we have a memory with minimum size as well as maximum size. So according to that, we are going to fix. This is going to be called as level 1, level 2, level 3. As you know that the previous slide shows that we have 64 KB, 1 MB, and then we have 1 TB or something like that. So depends upon that everything is going to be on chip in higher end processor. Based on that size, we are going to fix. This is going to be called as level 1, level 2, level 3. So all these things, why we are considering means according to that we are going to fix. This is going to be called as level 1. This is going to be called as level 2. This is going to be called as level 3. Okay. So even though we are going to fix this much size, we have to consider one more factor, that is going to be called as power. Whenever we are operating, whenever we are going to access that power, whenever we are talking about accessing that memory, so one thing I have to consider, what will be the power consideration. So that active power, whenever I am going to perform read as well as write, these are all the 2 operations we are going to perform along with the memory. Whether I am going to read from a memory or otherwise I am going to write into a memory. So in that case, that power is going to be static or dynamic, or just going to be that. So power is going to be static. Sometimes whenever we are going to use some kind of static RAM. Whenever we are going to talk about dynamic RAM, that is going to be called as dynamic power. Why? Because some refresher thing is required. We need some read operation is going to perform, write operation is going to perform, all those things. So in that case, the designer has to consider both the performance as well as power trade-off. So my ambition and my goal is I have to access as much cost, and then I have to go for affordable cost. Another one more thing, what will be the power consumption? What will be the power consumption? That is very important whenever we are talking about memory. So in that case, we are going to think about caches. So if I want to achieve these three things, cost, and then I want to have higher performance, and then I have to think about power leakage, some power consumption. So in that case, the best somewhat solution is caches. So that is why we have to study something about cache. So whenever we are going to use a word, it is not found in the cache. Whenever we are going to word, nothing but it is going to be a 8-bit, or it is going to be a 16-bit, or the 32-bit or 64-bit. It is nothing matter. So this depends upon the processor version, or the VK processor. So depends upon the processor. Okay. So in that case, it will check. Sometimes I will store it in my word. So the word must be fetched from lower level in the hierarchy and replaced in the cache. So what it will be means, so that whenever I am talking about the code that is going to be have the data that is going to be fetched, and then I am going to put it into the cache. Why? Repeatedly, if I am going to use that word, repeatedly if I am going to use that word, and then I am going to put it into the cache. So that is why it is first I will check for my data. If it is not available, I will go to the main memory, and then I will get the data, and then I will store it into the cache. So forget about that size of that. So as of now, we are going to consider a data, whether it may be 8-bit or 16-bit, 32-bit, or doesn't matter. But I will check for my data within the cache. If it is not available, I will go to the main memory, and then I will get the data, and then I will put it into the cache. So lower level may be another cache, or otherwise main memory. Sometimes if it is not available, level 1, I will check for level 2. If it is available, I will put it into the level 1. If it is not available, further I will check for level 3, or otherwise I will go to the main storage. So in that case, I will get the data, and then I will put it into that. So in that case, multiple words. So if I am again, I will tell you, a word is nothing but 8-bit or 16-bit. According to the processor configuration, you have to fix. But as of now, if I am going to multiple words, I am going to do combine, then it is going to be called as block, or a line, a single line. So multiple words is going to be considered as a block that is going to be moved for efficiency reason. So instead of accessing one by one, I will consider as a whole block. For example, I have word, I have a block that in that particular block, I'm going to have 4 words. So that is going to be 4 words combined is going to be considered as a one block that I'm going to move to a particular cache. So in that case, efficiency. Why? I will have 4 words in a particular. So that is going to, due to spatial locality, that are likely to be needed soon. So why? Because somewhere else it is far away. So in that case, what I will do, I will collect, and then I will put it into that. So block placement in a cache is going to be called a set associative principle. So I'm going to put a block, a group of word into a cache, then it is going to be called a set associative principle. A set is a group of blocks in the cache. That is the meaning. A set is nothing but a group of blocks in a cache. That is going to be called a set. So each block will have, sometimes first block I will have 4 words, second block I will have 10 words. It is not a matter, but a group of blocks. So block, again I will repeat, block is nothing but a group of words. A set is nothing but a group of blocks. Again I will repeat, if you have any doubts, you can ask me. A group of word is going to be called it as block. A group of block is going to be called it as set. Okay, any doubts here? Anyone can unmute and tell me you have any doubts between a block versus set? யாருக்காச்சும் டவுட் இருந்தா சொல்லுங்கப்பா, நான் திருப்பி சொல்றேன். Otherwise I can proceed. Hello? Hello? Anyone? And then unmute and then tell me. Okay. Whether it is clear, clarity.
Yes, sir.
Okay, thank you, ma. Next, I will block, a set of block is going to be mapped onto a set. So I have set 1, set 2, for example, block A, block B, block C. I will map to a set. So, and then I will place anywhere within that cells. First, I will map this group of blocks is mapped to a particular set. So we have 10 blocks, 1, 3, 5, 7. That is going to map to a set, set 1. And then after that, once after mapping is completed, and then I will put within anywhere within that particular set. So that is a option given to the designer. So first, I have 10 blocks. I have mapped 1, 3, 5, 7 to a particular set. After that, I will keep anywhere within that set. That is possible. So if I want to find a block, so what I will do? So in that case, I will have an address for each and every block. So that there will be some tag which is going to be there. So in that case, I will search along with the tag for in order to find a particular block within that particular set. So already I told you 1, 3, 5, 7. So one for that, for example, the block 1 will have one tag that will give you the address. So I will search with that address. So in that case, this particular block 1 is particular here. In that case, I will get that particular block. So that is there is a relationship block mod with the number of sets in that cache. So I have sets. So I have number of sets within that cache. Already I told you block set. Set is nothing but a group of block which is going to be stored in that cache. So I will have a block address. So with that tag, I will search where a particular, that is going to be the relationship. If I am going to have n blocks in that set, the cache placement is going to be called as n-way set associative. Already you all know what is meant by set associative. If I am going to have n blocks, then it is going to be called as n-way set associative. So there will be a direct mapping. That is going to be called as direct mapping. So if I am going to have only one block instead of n block, if I am going to have only one block, then it is going to be called as direct mapping cache. So block address modulus of number of blocks in that cache. So we are going to have only one single block that is going to be in that particular cache, then it is going to be called as direct mapping. Yeah, full associated cache just has one set, so block can be placed anywhere. So if I'm going to have only one block, but again I have an option, even though it is going to be one block, I can keep anywhere else within that particular set. So how I'm going to access that cache? Whenever I'm going to access that cache, there will be some complexity is going to be there. So whenever I'm going to read, it is very easy. So if I'm going to write, so in that case, I have to update, or otherwise I have to go for some other thing. So in that case, read is already it is stored. It is easy. So first I have to replace and then I have to write. So that and all it will take some time. So that is why always read is very easy. Copy in the cache and the memory will be identical. So cache writing is more difficult. So what it means, already we have to replace and then I have to write and then it will be kept. So for that only we are going to have two options. One is going to be called as write through cache. One is going to be called as write back cache. So already we have discussed in that unit 3. Anyone can tell me what is the difference between write through versus write back? This particular point I have given clarity or I have discussed in that unit 3. What is the difference between write through versus write back? Anyone? Unit 3 we have discussed what is the difference between write through versus write back. Whenever we are talking about that protocol, hardware protocol, snooping, directory based protocol.
So write through is updating both cache and memory. Write back is updating only cache.
Yeah, only updating the cache. Very good. Thank you. Very good. So in that case, we are going to have both write strategies going to have write buffer. So whenever we are talking about memory, always there will be something called as buffer. So already you all know what is the use of buffer. Temporarily I can store. So instead of every time I'm going to access to that main memory, I will put it into the buffer. So in that case, that the main memory will be used for some other purpose. So if you all know, I'm going to take one practical example. If I'm going to take printout. So if I'm going to take 10 copies, 10 pages. So just I will give print. So first the printer will take one by one. It won't go to the main memory taking the second page, third page. Just not like that. If it will keep all the copies in the print buffer. So that is kept everywhere. So both write strategies can use write buffer to allow the cache to proceed as soon as data are placed. Once the data is given, automatically it will be placed. Once that number of copies is given, automatically it will be stored in the buffer. Now coming to the mesh rate. What is miss rate? I told you miss rate versus miss penalty. Measure the benefits of different catch. Number of access miss divided by number of. So I'm going to access a particular data. If it is not available, so that is going to be called as miss rate. I'm going to access one particular instruction. So it is not available within the catch. So in that case, that is going to be called as miss rate. How many times I have access? How many times I get immediately? How many times I'm not getting? According to that, that is going to be called as miss rate. So there is going to be C3C model. We are going to compulsory, capacity, conflict. What is compulsory? So whenever we are going to access a particular catch instruction, the miss that occur, that first reference to a word when the catch is empty. So that there is no instruction is available. The catch is entirely empty. But even though it is going to be infinite size, compulsory, which means that there will be, we will get a catch miss. Or otherwise, sometimes capacity. So if I'm going to get that instruction, but it is not available, but even though there is some blocks are available, because for example, I have 10 for example, one application it will have 10 blocks, but I have a capacity to have a 5 blocks only in that catch. Carefully listen to this example. For a particular application, I have 10 blocks, but I have 5 blocks can be kept in a catch 1. So in that case, I will check for a particular block. The word, it is not available. Why? That 5 blocks is only, but that it is available in several 6 or 7 block. So even though I have some capacity, but I have some, due to some boundary, there will be miss occurs. Or otherwise, conflict, if the block placement strategy is not full associative. What is meant by not full associative? Full associative means only one block will be available. So in that case, there will be some conflict occurs. In that case also, it is not possible. Occurs when several blocks are mapped to the same set or otherwise block frame, something like that. So there will be some conflict over mapping, something like that. So in that case, I will have miss. So in that case, or otherwise, I will have multi-threading or multi-core. That is going to be the 4th C. So we have a catch coherency. Already I told you. So same memory location will be shared by some other people. So in that case, so there will be some catch coherency issue will be there. How the catch coherency will be avoided with the help of snooping based or directory based, we have discussed all those things. So in that case, they will have some relationship they have given. Miss. Normally people will think, the designer will think about how many number of instruction I have missed. So miss divided by number of instructions. Miss rate into memory access divided by instruction count. So miss rate into memory access divided by the instruction. So these are all the relationship. So we have something called as hit time. So hit time immediately I got. Sometimes I will miss something going to be called as miss penalty. I'll tell you what is basically miss penalty is. For example, what is basically miss penalty means. So if it is not available, so I have some, for example, I have some time to keep that particular block inside. So for example, I tell you one simple thing. I have 5 blocks, but I have totally 10 blocks. I have kept 5 blocks. So what it means, I want to get some information. So in that case, it is not available in that level 1. What I will do, just I will replace from level 2 to level 1. That is going to be called as miss penalty. So just there will be some time for replacing that block. So that is going to be called as miss penalty. So in that case, reducing that miss rate, I want to reduce that miss rate. How I can? So sometimes I will go for larger block size. What is mean by larger block size? Larger block size means I can put more number of words. Or otherwise, I will have larger catch size, level 1 catch, and then I will go for higher associative. Associative means more number of sets I have to put there. So in that case, I can I can reduce the miss rate. Or otherwise, I will go for reducing the miss penalty. Just now I told you. So for example, how I can reduce the miss penalty. So if you have a larger catch, multi-level catcher. So in that case, for example, instead of taking from disk storage to that catch, so in that case it will take much time. So in that case, I will increase that multiple levels. So in that case, somewhat I can reduce. So instead of go to the main storage, this storage, I will have it in the level 3 or something, level 3 or something like that. So I can try it to reduce that miss penalty. So reducing the hit time. So avoid the address translation. So what is meant by address translation is, I'll tell you soon. I will tell you address translation. Now I don't want to confuse here. But hit time is nothing but how can reduce the hit time means I will check for a particular memory block which is available, then it is going to be hit. But it will take some time. It will take some time for in order to get that, even though it is available. So that is going to be called as avoid address translation. What is mean by avoid translation means, so already I told you that according to that processor, it will know only main memory. But sometimes the designer will use virtual memory. So what is virtual memory? So there will be some memory that is used every time and cannot put all the code in that particular main memory. So I will keep it in a virtual memory. So whenever I need only that particular portion, whatever the current requirement, that alone I will keep it in a main memory. So in that case, if I'm going to have kept in a virtual memory, I have to translate that a virtual memory address to physical memory address. So that time is going to be called as translation time, avoiding address translation. So that processor takes some time converting that virtual memory address to physical memory address. Only the processor knows physical memory address. So even though it is available, but it is available in the physical memory, we have to avoid some reducing the hit time. So avoid address translation. So kept as fast in that main memory. So we have some 6 basic cache optimization, what we have discussed. So for larger block size, what is the larger reduce the miss rate? How to avoid larger block size? So we have some spatial equality, lower miss rate. So that block size is going to be more. In that case, I can put more number of words. So it will reduce the compulsory misses. So which means that we bring more words. That's why just now I told you I can keep more words. Then I can avoid compulsory miss. So miss rate. So the number of blocks, miss rate, the number of linear cache will become small. So the number of blocks. So if I'm going to keep very minimum number of blocks, automatically miss rates will happen. So in that case, we have to have some great deal competition along those blocks. So how to optimize? How optimizely we have to know. These are all the things are repeatedly use. According to that, I have to keep that blocks, and then we can increase the capacity in order to avoid misses. So this is that. For example, different size, different percentage. So based on that, I can reduce the miss rate. So in that case, otherwise I will go for bigger caches. So either we are going to increase the block size. Already I told you bigger caches. So we can accommodate more number of blocks. So in that case, I can reduce the miss rate. So but what happen means it indirectly it will increase the cost. So that is one more thing. And then we have power consumption also, it is going to be more. So otherwise we are going to have higher associative to reduce the miss rate. So reduce the higher associative means we have kept it into a single block and then that is going to be mapped. So otherwise we will go for multi-level caches. So instead of I will have multiple level caches means level 1 will have some size, level 2 will have some size, level 3 will have some size. So in that case, what we can do means instead of going to that main memory, we can with the help of different levels of cache, I can reduce the time, the miss rate. So that is why this relationship time is going to be that given in this particular. I think it is easily. So we have hit time. You know what is miss rate, what is going to be miss penalty, all those things already you all know. We have to, for example, we have to summarize that definition. According to that, we can come out with that particular relationship. So here we have. So already I told you. So we have for example, we have some conflict. So or otherwise we will have some complexity whenever we are going to read, or otherwise whenever we are going to write. So in that case, we are going to have write buffer. Again, we are read as well as write. So if you take this particular code, we have to make that buffer empty. So then only I can easily put that word, or otherwise I can write into that one. So in that case, why we am going to put the buffer empty means, so in that case I can easily write. So in that, in order to try to avoid that conflict, we are going to use that one. Or otherwise, so check write buffer. So we can use buffer, and then from the buffer I can store that information. Then we can reduce the miss penalty. So we have some write back. We all know dirty bit. So already what is mean by dirty bit, we all know. So dirty bit is nothing but, for example, that particular block is named that exclusive state. So that is why it is going to be dirty bit. So it has to be updated to HN. So for example, whenever we have a read miss transaction, what is mean by read miss transaction? I will search for a word which is not available in the do catch catch. Then I am going to have a read miss transaction. So that will now, it will be come along with the write bit. So finally, we are going to, in that 6 optimization, we are going to see all the avoid address translation. What is address translation? Already I told you, we have some virtual address that must be mapped to a physical address. So we have some virtual address that has to be converted into physical address. Based on that, I can avoid translation with the reduced hit. So the catch may be either use virtual or physical address. So in that case, I have to reduce the translation time according to that. So I reduce the miss penalty. So not reducing the miss penalty means reduce the time for miss penalty. So in that case, I can easily avoid the translation. According to that, I can increase the hit rate. Okay, so this is the topics comes under memory hierarchy. And one more topic that is a memory hierarchy optimization is there. That is this is the things comes under this one. So you have to refer your chapter 2 for this particular topic. Okay, so next class we will move on to the next topic in your unit 4. Any doubts? Already I told you, if you have any doubts, you can watch the video, and then you just note down. If we have some refresher class at that time, we can ask. Okay. So one more announcement I want to tell you. Like Wednesday, as of now, you are going to have exam on unit 3. So somebody asked about what are the lectures. Today I have posted up to warehouse scale computer in my class. So I have keep that video also in that class. So you just go through the some problems related with snooping based, directory based, and then PDF is also, all those things are given in that class. So you just go through, according to that you prepare. Anything else?
Sir, only MCQs, right, sir?
Not MCQ, sometimes that descriptive also one time. So normally we'll have one, we have MCQ as well as descriptive. That pattern is following, the same pattern is going to be followed.
One descriptive and all MCQ, sir.
Hello?
One descriptive and all
No,
MCQ.
No, because I didn't set that question paper. It will be a collection. So what we have followed, no, exam 1, exam 2. But we everything you can finish within that hour. That is a confirmation I can give you now. So we allot 1 hour or otherwise 1 hour 15 minutes sometime. Within that time schedule, you can easily complete that. But you have to prepare for both. So if you completely, if you read that third unit, definitely you can be able to answer for both the things. But everything according to the time limit only, we will fix the question. Any other thing? So if you are well prepared with that exam questions, then it is easy for you to write the end semester examination. That thing we will assure you. So if you practice the question, already we have given the solution. I think in my class also I have posted that questions. Otherwise I will check. If it is not there, I will post it. Okay. So in that case, you can get good marks. Any other thing?
Sir, is the test during class hours?
Yeah, maximum almost I will, because the decision is not taken by, I have to ask thing, but everything will be tomorrow class, we will confirm you.
Okay, sir.
We will put it in GCR in advance. Any other thing? So in that case, you can leave. Thank you.
Thank you.